Thank you very much. My name is Cristiano Longarini, and I'm a postdoc at the University of Cambridge. I'm really happy to be here and to speak during your seminar. And so my topic of research is protoplanetary disk and planet formation. And what I'm going to talk about today is the role of gravitational instability in protostellar disk evolution and planet formation. This is the work I've been doing during my PhD and at the University of Milan, and what I'm currently doing right now in my postdoc. So first of all, why are we interested in protostellar disks? So protostellar disks are astrophysical objects that are very important since they are linked between star and planet formation. Indeed, they form with the star, and they are the environments where planet formation takes place. So in this movie, I'm showing you an hydrodynamical simulation performed by Matthew Bate. And this is a hydrodynamical simulation of star formation. And what you can see in these small movies is that whenever we form a star in a molecular cloud, during molecular cloud collapse, there is also the formation of an accretion disk. So the material around the protostar has this shape. And what is really important to note here is that the star formation process is a really chaotic process. So as you can see, there are a lot of dynamical interaction between different protostars, and also the role of the environment is really important in shaping protoplanetary disks. And so taking into account all of this is very important when we are studying planet formation. And so just to give a brief outlook of protostellar disk classifications. So this is like an historical classification for these objects, and it's possible to divide these objects in 4 classes, and they are kind of tracing the temporal evolution of these objects. So we have, first of all, class 0 objects, where we have a molecular cloud core that is still collapsing. We have a central protostar, but there is a lot of material of the molecular cloud that is shielding the emission of the protostar. And so when we look at the spectral energy distribution, we see just a cold black body emission in the far infrared wavelength. Then we have class 1 objects. These objects are composed of a central protostar and an accretion disk around them, but there is still the molecular envelope that is interacting with the disk. And so in the spectral energy distribution, we observe a black body of the protostar, but with a strong infrared excess, because we still have cold material surrounding this. Then we have class 2 objects that are the most important ones, since they are the ones that we can observe very well with ALMA. And these objects are composed of the protostar and an accretion disk around them. So the molecular envelope is not affecting the emission of these objects. And when we look at the spectral energy distribution, we basically see the stellar black body with a near-infrared excess that is the effect of the accretion disk that is absorbing the protostellar radiation and re-emitting it at longer wavelengths, since the material is cold. And finally, we have class 3 disks that are basically main sequence star with the remnant of an accretion disk. And so this is what we can do with ALMA. So ALMA is a radio interferometer that allows us to spatially and spectrally resolve the emission from a planet-forming environment. And in particular, this is a collection of dust emission coming from planet-forming environment. This is the D-sharp sample of protoplanetary disks. So these are very bright disks that have been studied with very high resolution. And what we can see here is that these disks are not smooth at all. They show substructures such as rings, gaps, spiral, non-axis symmetric features. And so this means that the environment in these disks is chaotic. There are a lot of physical processes happening there. And one possible way to explain protoplanetary disk substructures is planet-disk interaction. Meaning that the interaction between the protoplanet and the accretion disk is creating this substructure. So a protoplanet is able to carve a gap or to excite spiral arms, for example. And but if we really look into the presence of embedded protoplanets in this disk, we can have the indirect or direct detection of these bodies. So first of all, if we want to indirectly investigate the presence of embedded protoplanet, what we can do is to hydrodynamical modeling these sources. So the idea is that we want to reproduce the emission, the morphology of these disks by simulating planet-disk interaction with hydrodynamical codes. And this is, for example, the case of DH tau in the top left of this slide. Then, during the last few years, a lot of interest came around the kinematics of protostellar disks, so studying the velocity field of protostellar disks. And what we can see is that there are kinematic signatures of planet-disk interaction that is possible to observe thanks to ALMA. And here I'm showing you two examples of these signatures. And the idea is that the protoplanet is interacting with the protoplanetary disk material, perturbing it, and we are able to observe these perturbations. And finally, for just a couple of cases, we can directly image embedded protoplanets in circumstellar disks. The most famous case is PDS-70. This is an ALMA image of dust continuum emission in PDS-70, where it is possible even to resolve the circumplanetary material. And then we another example is HD 169142. So these are scattered light images, and he and here at Monash found this blob that is moving with the Keplerian velocity, and this blob is exactly inside the gap of dust continuum emission, pointing to the fact that there is a protoplanet that is carving this gap and is moving with Keplerian velocity. And so, I mean, if we really believe that in those disks there are protoplanets and that the substructure we observe are created by protoplanets, the consequence is that planet formation must happen very fast and very early during the disk lifetime. And when a disk is young, the physical processes happening inside them are different, and we need to take into account additional effects. For example, this is a very interesting plot. So it is showing the cumulative mass distribution of protoplanetary disks in different star-forming regions according to their age. And what we can see is that there is a trend with the star-forming region age, meaning that the younger star-forming regions, such as Orion, show a cumulative mass function that is shifted towards higher value of mass, of disk mass. And this basically means that younger disks are, in general, more massive. This makes sense because they are accretion disks, so most of the mass has not yet been accreted by the central object. But when a disk is massive, what we need to take into account is the possible role of self-gravity and gravitational instability. And so the main question of my work is to understand what is the role of self-gravity and gravitational instability in disk evolution and in the process of planet formation. So what are self-gravity and gravitational instability? So what are we talking about in the context of protoplanetary disks? So in general, an astrophysical body is self-gravitating whenever its mass is high enough to contribute to the total gravitational potential. And this threshold for protoplanetary disk corresponds to a disk-to-star mass ratio of about 5%. So when the disk mass is about 5% of the stellar mass, the dynamical effects of self-gravity becomes important, and we need to take into account it. So self-gravity modifies the hydrostatic equilibrium of a disk, and in particular, we can show that the hydrostatic height of a self-gravitating disk is different compared to a non-self-gravitating one. And also the centrifugal balance of such disks change. And in particular, what it is possible to show is that when we compute the azimuthal velocity of these disks, there is a correction due to the presence of the disk gravitational potential, and this correction makes the rotation curve super Keplerian, meaning that this term is accelerating the gas particles in protoplanetary disks. And just to follow up a bit about this, so this super Keplerian contribution due to the disk self-gravity is really important since it can give us a direct way to investigate protoplanetary disk masses. Of course, this is something we can just apply for massive disks. So let's say the typical protoplanetary disk is not massive, but for massive disk it is possible to apply this method. And so the idea is that if we sketch the rotation curve for this protoplanetary disk and we increase the disk mass, what we can see from the plot on the left is that the outer part of the curve has a higher velocity according to the disk mass. And we applied this method to so far to 6 sources, and we also benchmarked these against hydrodynamical and radiative transfer simulations. And a couple of works showed that this is a reliable way to estimate disk masses, and the minimum disk to star mass ratio we can measure is of the order of 5%. And yeah, so far it has been applied to 6 sources, but there are more to come with the new ExoALMA data. And so as for gravitational instability, so gravitational instability is just a linear hydrodynamical instability that can arise in self-gravitating systems. And this has been studied a lot in the context of galactic dynamics. Indeed, this is the dispersion relation used also in the field of galactic dynamics. But here in this equation, there are all the important ingredients we need to take into account when we consider gravitational instability. In particular, there are in the disk, there are stabilizing and destabilizing effects. In particular, the sound speed, so the pressure, it's a stabilizing effect for the disk, meaning that the pressure tends to expand the disk, so it's like preventing the collapse. Then we have the surface density, so the term that is proportional to sigma, that is like proportional to the disk mass, and this is the self-gravitating term itself, so it tends to destabilize the system. And finally, we have the epicyclic frequency that, in the case of a Keplerian disk, is just the Keplerian frequency. That is a stabilizing effect. So the idea is that the rotation of a disk tends to stabilize it because of the centrifugal force. And so it is possible to study when gravitational instability happens in protoplanetary disks and by studying the sign of the dispersion relation. But in general, what is important to take into account here is that this parameter Q, this is a dimensionless parameter that completely controls the onset of gravitational instability. And as you can see, this parameter that is called the Tumri parameter is the ratio between the stabilizing terms, so pressure and rotation, over the destabilizing term that is, in this case, that is self-gravity. And the instability threshold here is Q equal 1. As I told you, so this parameter is basically controlling when gravitational instability takes place. And now we want to understand how it is possible to trigger gravitational instability. So what should we do to make a disk gravitationally unstable? And the idea is that we can do 2 things. So the first one is to cool the disk, so to decrease the sound speed. And this is a typical approach in numerical simulations, since it is very easy to implement in numerical codes, even though it's not so realistic, but it can give us an idea of how it works, how gravitational instability works. So the idea is that we cool gas particles in the disk with a given cooling prescription. In this case, we prescribe the cooling time to be proportional to the dynamical time with a constant of proportionality beta. This is, of course, not realistic, but it's just giving us an idea of how it works. And finally, there is a second way in which we can trigger gravitational instability. This is by adding mass, so by increasing the surface density. So this has been studied in the past. It's not, let's say, not so popular as the beta cooling, and it has just been studied in the context of star formation. So here, the numerical simulations that have been performed were the simulation were a star formation, star plus disk simulation. So the idea is that they had a molecular cloud collapsing, and this collapse is mediated through a disk. And this is the way in which the disk mass is increased. Okay, so this is just a schematic view of what is the outcome of gravitational instability, and I'm going to guide you through this journey. So if we start with a stable disk and we want to trigger gravitational instability, we can either cool the disk or adding mass. So a first outcome of this process is fragmentation, meaning that if we cool the disk too fast, so if our beta is too small, or if we add too much mass, we end up in fragmenting the disk. So the idea is that the disk becomes unstable, develops a spiral pattern, but the disk becomes or too cool, or too cold, or too massive, and so this spiral will fragment. And this is the first outcome of gravitational instability, while a second possible outcome is that we get a self-regulated state. So if the cooling is not so fast, or if we don't add too much mass, we obtain self-regulation, meaning that the amplitude of the spiral perturbation remains constant, and this spiral is able to transport angular momentum. And this transport of angular momentum can be described with an alpha framework, where alpha is the Shakura-Sunyaev coefficient. And here I'm just showing you two simulations. So on the left, we have the self-regulated state, while on the right, we have the fragmenting state. So I can play it again. So you can see that in the self-regulated case, the spiral, the amplitude of the spiral is constant, while in the fragmenting case, we form this gravitationally bounded object. So I'm mostly interested in the self-regulated case, so where we don't observe fragmentation. And in this case, the spiral perturbation can efficiently transport angular momentum. In general, so accretion in protostellar disk is possible thanks to the viscosity. And protostellar disks are differentially rotating, meaning that between two neighboring rings of protoplanetary disk, there is a viscous friction because they are rotating at different speed. And what we usually do to describe the viscosity is to use this prescription, that is the alpha prescription of Shakura-Sunyaev, where alpha is a dimensionless number that is measuring the efficiency of angular momentum transport, or equivalently our ignorance about the actual source of the viscosity, because we really don't know what is the actual source of the viscosity in those systems. And so, as I told you before, for a self-regulated gravitationally unstable disks, it is possible to transport angular momentum. And it is possible to describe this transport angular momentum through an alpha that we will call alpha GI, that is proportional to delta sigma over sigma to the power of 2, where delta sigma is the amplitude of the spiral perturbation. So this is always valid regardless of the source of self-regulation that can be either cooling or adding mass. It's possible then to connect this delta sigma over sigma with the two different paths to self-regulation. But the transport of angular momentum does not take into account the source of self-regulation. And this is important because it's a more general argument. And finally, last thing I would like to show you about gravitationally unstable disks is that the morphology of the spiral can change as a function of the disk parameters, and in particular as a function of the disk to star mass ratio. You can see that more massive disks tend to show fewer spiral arms, and this will be very important in the final part of this talk. So now I would like to discuss about the first big topic of this seminar, that is the transport of angular momentum in gravitationally unstable disks, and how this is connected to the protoplanetary disk kinematics. So, a hot topic in protostellar disks during the last few years is the protostellar disk kinematics. So, in protostellar disks, there are molecular tracers that are usually CO isotopologues, and this tracer emits with a line emission. And so, by knowing the rest frequency of this emission, we can measure the Doppler shift of molecular lines thanks to ALMA. And with this, we can map the velocity field of these objects. And in particular, just to give you an idea of the order of magnitudes of the velocity we're talking about here. So the azimuthal velocity of protostellar disk at 0th order is just a Keplerian velocity, and its magnitude is of the order of the kilometer per second. Then we can have radial velocities, and here I'm just showing you what is the radial velocity, just the accretion one, so the one driven by alpha viscosity. And you can see that for typical values is a fraction of the meter per second, so it's not really really big. And finally, we have thermal motion, so the sound speed that is of the order of hundreds meters per second. So as you can see here, the most important velocity component is the azimuthal one, that is basically determining the shape of this observed velocity field. But on the top of this smooth disk that rotates at an almost Keplerian velocity, we can observe non-Keplerian kinematic signatures that are pointing to physical processes happening inside these systems. For example, embedded protoplanets can perturb the velocity field of protoplanetary disks, but also the presence of a stellar companion and also hydrodynamical instabilities can perturb the velocity field. And what I'm mostly interested in is how gravitational instability perturbs the kinematics of disks. And in particular, so in 2020, Cassandra Hall found that gravitational instability has clear kinematic signatures in molecular line emission. And she studied this problem through hydrodynamical simulations and radiative transfer. And she observed that gravitational instability perturbs globally the disk. So in every let's say in every point of the disk and also in every channel, so in every velocity. And this perturbation is called the GI wiggle, since it is like an oscillation. And the shape of this perturbation is determined by the characteristics of the spiral. So how many spiral arms do we have, the opening angle, and also the amplitude of the spiral. What we have done in 2021 was to study the GI wiggles under an analytical perspective to understand how the perturbation is related to the disk's parameter and to see if we can learn something by measuring these perturbations. So since gravitational instability is basically a spiral density wave, it also perturbs, this wave can also perturb the velocity field. And to understand how the density and the velocity perturbations are related, we need to solve the fluid equations. So we took the fluid equations, we perturbed them, and then we obtained the radial and azimuthal velocity field, component of the velocity field, under a given hypothesis. So here we are considering just a thin disk that is marginally unstable, so with the 200 parameter equal 1. That is in self-regulated regime, meaning that the delta sigma, so the density perturbation, is given by alpha, so by the amount of angular momentum that is transported. And we are considering an early Keplerian disk. And you can see here I'm showing you the radial and the azimuthal component of the velocity field. And you can see that so the main scaling is with the Keplerian velocity. Then we have a term that is related to the disk to star mass ratio. We have alpha, so the amount of angular momentum, and also we have m, where m is just the number of spiral arms. And from these analytical equations, we can sketch the analytical velocity fields, and this is an example for a given set of parameters. And as you can see, the perturbation is global, so it's visible everywhere and in every channel. So it's like as in the numerical simulations I showed you before. And if we focus our attention onto the central channel, so the vertical line, so in the first of the 4 plots, it is interesting to look at it because it's not a straight line. It shows this oscillation, while for a simply Keplerian disk, it's just a straight line. And we observe like an oscillation here because we have a perturbation to the radial velocity. So we compared our analytical model with numerical simulations. We did it a couple of times, actually. This is one of the last comparisons we did. This is a paper that is about to be accepted. And so on the top row, we have the analytical model, so the surface density, so just the spiral, the line of sight velocity, the residuals, so the residuals are just the observed velocity field minus the anaxisymmetric Keplerian velocity field, and finally the radial velocity. And we compare these with numerical simulations performed with Phantom and then post-processed with MC-FOST. And this is just a by-eye comparison, and the two the model matches with the simulations. We also did like a quantitative comparison, and the level of agreement is pretty good, meaning that our analytical model is overall good to describe simulations. But so what's interesting here is that, as I showed you before, the magnitude of the perturbation depends on alpha, so depends on how much angular momentum the spiral is transporting. But the problem here is that the amplitude of the perturbation scales also with the disk to star mass ratio. So a more massive disks or a disk that is transporting more angular momentum are contributing in the same way to the amplitude of the perturbation. And so in order to constrain alpha, so to constrain the angular momentum transport in those disks, we need to break this degeneracy. And actually, I mean, since these disks are gravitationally unstable, are really massive, and it is possible to use the rotation curve method I showed you before to break this degeneracy. And when we fix the disk mass, the amplitude of the wiggle, so the amplitude of this perturbation in the velocity space, scales as the square root of alpha. And so if we know the disk mass and if we measure the amplitude of the perturbation, we can in principle constrain the alpha viscosity. So now I'm going to show you two examples where this was possible. So the first case is LIS-227. LIS-227 is a young disk, so less than 1 million year, that shows two spiral arms in dust continuum emission. This disk has been studied a lot in the past. It was also part of the D-sharp sample. And between 2017, 2018, a couple of works showed with the hydrodynamical simulations that the morphology of these disks can be reproduced by gravitational instability, while it is not possible to reproduce the same morphology with an embedded protoplanet. And in 2021, Teresa Paneque Carreño presented new kinematic data of these disks and found that there are global kinematic signatures in the velocity field that are co-located with the spirals, and so suggesting the possibility to be GI wiggles. And the same year, with the rotation curve method, Benedetta Veronesi measured the disk mass of LIS-227, finding that the disk to star mass ratio for this system is about 17%. So this is definitely in the self-gravitating regime. And so what we have done in a paper that has been just published is that, I mean, this system is unique because we know basically everything, and we observe GI wiggles, and so we can constrain the amount of angular momentum that the spirals are transporting. And in particular, the degeneracy between disk mass and alpha is broken since we know the disk mass. And so we took the central channel of the velocity field, we measured its amplitude, and with this we could constrain alpha. And in this case, alpha is 0.038. And what I want to stress here again is that this estimate is regardless of the path to gravitational instability. So this can be caused by cooling, this can be caused by infall, but the estimate of alpha doesn't care about this. And to compare this value with something we can actually measure, we use the viscous theory, and according to the self-similar solution, it is possible to connect the alpha viscosity and disk parameters with the expected accretion rate onto the central object. And the accretion rate is something we can measure. And we have a measurement of this accretion rate that is 10 to the minus 7.2 solar masses per year. And since we know alpha and we know the temperature of the disk and we know the disk mass, we could compare the expected value from our kinematic study with the actual one we measure. So our estimated value is 10 to the minus 6.9 solar masses per year. That is within the error bar of the measured value, and the agreement is, I must admit, is pretty good. And so this is another, let's say, another proof that gravitational instability may be responsible for angular momentum transport in LIS-227. And now I want to talk about the second source we have been analyzing during the last month. So it's a Biaurighe. A Biaurighe, it's a class 2 disk, so it's an older disk compared to LIS-227. And but this disk is interesting because it's in a crowded region of the molecular cloud, and it shows interaction with the environment and shows also sign of infall. And so for this reason could be an interesting target for gravitational instability. And in addition to that, in scattered light images, it is possible to observe beautiful spiral arms. And for this reason, in 2021, we proposed the ALMA observations for this disk. The proposal was accepted. The PI was Robin Dong. And the main the idea of this proposal was to look for gravitational instability and possibly GI wiggles in the kinematics of a biorig. So these are the 13CO data. So this is the moment one map for a biorig on the left. And as you can see, as the arrow is pointing to, there is this, the central channel of the emission shows this oscillation that, I mean, the morphology is pretty similar to a GI wiggle. And if we, in the left panel of this slide, there are the residuals. So there we are just subtracting to the observed field an axisymmetric Keplerian one in order to enhance the non-Keplerian signatures. And as you can see, these non-Keplerian signatures are following the position of the spirals. So we try to do the same as we did for Elias 227. The problem here is that we don't have a reliable disk mass estimate, since the source is almost face-on, so it has a low inclination. So it was not possible to properly extract the rotation curve and to apply the rotation curve method. So what we can give here is just a couple of disk-to-star mass ratio and alpha viscosity values that are able to reproduce the amplitude of this perturbation. So on the left panel, I'm showing you the perturbation, the GI wiggle for the 13CO and C18O with the yellow curve, and the gray curve is our analytical model. And in the right part of this slide, I'm showing you a plot of the disk-to-star mass ratio against alpha viscosity, and the yellow line is the line where the solution lies. And in particular, what we can do here is just to give like a range of possible values. That is the one inside this square. So what we say is that basically the viscosity is lower than 1. That makes sense, of course. And that the disk-to-star mass ratio must be smaller than 0.3, 0.4, because otherwise, I mean, the mass would be too high. And so this, let's say, is the range in which we think that the disk-to-star mass ratio and the alpha viscosity are for a biorig. Okay, so this is, now I want to talk about the second topic of the seminar, that is planet formation in gravitationally unstable disks. And when we talk about planet formation, what we need to introduce is the dust component and the aerodynamical interaction between gas and dust. So protoplanetary disks are composed of gas and dust with a mass ratio of 100 to 1. And these two components are aerodynamically coupled. And the dust is really important in the process of planet formation, since it allows to form rocky planets or planetary cores. And so, as I told you, gas and dust are aerodynamically coupled in protoplanetary disks, and they are coupled through a drag force. And the typical time scale for drag force to act is called stopping time. And the stopping time is related to the grain size, so to the physical size of dust particles. But what's, let's say, what is better to study is the Stokes number. So the Stokes number is just a dimensionless measurement of the aerodynamical coupling between gas and dust. And it is the ratio between the stopping time and the dynamical time of the system. So the ratio between the drag force time with the typical time scale of a particle in a disk, that is the dynamical time. And there are three main regimes of Stokes number. So when the Stokes number is very low, means that the grain size is really small, and dust particles are strongly coupled to the gas. And so the dynamics is pretty much the same. Then for Stokes number of the order of 1, dust particles are marginally coupled, and this is the most interesting regime, since the drag force time scale is comparable with the typical evolution time scale, that is the dynamical one. And many interesting phenomena can happen in this regime. And finally, we have the large Stokes number regime, where the dust particles are uncoupled. They are too big, so dust particles are too big to feel drag force, and so basically they do not interact with the gas. What I'm interested here is the interplay between dust dynamics and gravitational instability. So in principle, if one wants to study gravitational instability in a multi-fluid system, it's very painful because one needs to study the fluid equations of a coupled system. So we did a bit of analytical work about this in 2023, but I don't want to bother you with analytical calculations. So I want just to give you the main message of this work. So in order to understand whether dust can be unstable to gravitational instability, it is possible to define the Tumri parameter for dust, that is like the equivalent of the one we used before, where we have CD, that is the dust velocity dispersion, and sigma D, that is the dust surface density. So what happens in a gravitationally unstable disk to the dust? So the dust tends to collect inside gas spiral arms, and the maximum effect is for Stokes equal 1, so the interesting regime I was talking about before. And the concentration of dust particles inside gas spiral arms can be very high, that the density of the dust can be comparable to the gas one. And so these gas spiral arms are a location where dust particles are in principle able to collapse because they can reach very high density. But in order to prevent collapse, the dust has also a velocity dispersion. So in our when we study dust, we usually model it as a pressureless fluid, so it has no thermal motions. But what the dust can develop is like a velocity dispersion, so random motions, and these motions are generated because of the interaction with the gas. And it is possible to measure the degree of dust excitation, so how much the velocity dispersion of dust particle is important. And it has been shown in the past that it depends on the aerodynamical couplings, on the Stokes number, and also on the morphology of the spiral. So in this slide, I'm showing you the effect of dust trapping inside gas spiral arms. So these are 8 snapshots of dust density for different Stokes number, ranging from 10 to the minus 3 to 100. And so for small Stokes numbers, so 10 to the minus 3, 10 to the minus 2, we see that dust is basically tracing what is tracing the gas. So it is possible to observe spiral arms also in the dust density. While when we go towards a higher value of Stokes number, so between 0.1 and 1, you can see that the spiral traced by the dust are thinner because the dust is more concentrated inside these structures. And while the Stokes number, when the Stokes number is higher than 1, so for 5, 10, or 100, this density contrast diminishes, and eventually for Stokes equal 100, it is difficult to observe the spiral pattern because the particles are too uncoupled. So, and as for the dust excitation, so as I told you before, dust can get excited when it interacts with spiral arms. And in particular, the effect of the spiral arm is to give a kick to dust particles and so to excite because of it. And the level of excitement depends on a couple of parameters. So it depends, of course, on the Stokes number, so how much the dust particles are coupled to the gas. Depends on the strength of the spiral perturbation, so the delta sigma over sigma, that is related to the alpha, as I showed you before, and also is related to the number of spiral arms, because it's basically the number of kicks dust particles receive, and so it is related to the disk to star mass ratio. And in particular, so a dust particle is efficiently excited when it receives a stronger kick, so when alpha is higher, so when the angular momentum that is transported is higher. Then for low disk to star mass ratio, because the number of spiral arms is higher, so dust receives more kick. And finally, for high Stokes number, because if the particles are more uncoupled, it is easier to excite them. And so we, in 2023, we performed the numerical simulations of gas and dust in gravitationally unstable disks, and we wanted to see whether dust collapse was possible inside the spiral arms. So we explored as much as possible the parameter space, And what we see is that for a subset of our simulation, dust collapse is actually happening. And in particular, it happens for high disk to star mass ratio, as expected, when the viscosity is relatively small. So I say relatively small because this value is actually high. But for a gravitationally unstable disk, this means that the delta sigma over sigma is not so big. And finally, for Stokes of the order of 1 particles, so for particles that are marginally coupled. And in particular, it's possible to measure the mass of this dust clump to be of the order of the Earth mass. So it is actually a planetary core. And from this plot, I'm showing you the average density of gas and dust in this simulation. And as you can see, only the dust component is collapsing, while the dust is not. So this is actually a formation of an actual planetary core made up of dust. And just want to spend a couple of words on what happens after to these planetary cores. So we show that it is possible to form planetary cores, so 1 to 10 Earth masses, objects in the outer disk of a very massive disk. And, but this core will eventually undergo planet migration. So the problem is that planet migration for such light planets is really fast. And so we expect these planets to drift toward the central object very fast, but at the same time, the disk is really massive. And so the possibility for these cores to accrete materials is really high. And so they can increase their mass a lot in a small time scale, eventually stopping migration. And we performed several numerical simulations to study different regimes. And in particular, here I'm showing you a simulation where the accretion time scale is of the order of the migration time scale. And so for a 10 Earth mass planetary core in the outer disk. So as you can see in this first part, the core is undergoing planet migration, so it's drifting toward the central object, but its mass is increasing more and more, and eventually it's high enough to carve a gap and stop migration. And it is possible to see this behavior also in plots where I'm plotting the radius of the planet and the mass of the planet as a function of time. And you can see that the radius of the planets tend to decrease, but then it stalls because the planet reached the thermal mass, that is the orange line in the right plot. So when the thermal mass is reached, it can open a gap and eventually stop migration. So these are my conclusions. So briefly, the kinematic signature of gravitational instability allows to measure the amount of angular momentum that is transported through GI. And we are now trying to understand if it is possible to extend our study to other sources, maybe to class 1 objects, so to younger objects. Then self-gravity, as I showed you, is a direct way, give us a direct way to measure protoplanetary disk masses when the disk is sufficiently massive. And what we are doing now is to apply this method for the ExoALMA sample. ExoALMA is an ALMA large program, so new data of protoplanetary disks. And as I showed you, the interplay between dust dynamics and gravitational instability give us a way to explain planetary core formation in young systems. And what we are interested now is to better characterize the early evolution of this cores. And then something I'm doing now, actually, with the help of Daniel, is to investigate different paths to trigger gravitational instability. And I'm just leaving you with this plot where we implemented in Phantom a possibility to inject mass in a protoplanetary disk in order to trigger gravitational instability rather than cooling the disk. And we are testing self-regulation, the transport of angular momentum, and we are also want to characterize better the morphology of these systems. So yeah, with this I finish my talk, and I'm happy to take questions. Thank you.
In your simulation of that planetary core formation, how long do those 1 Earth mass planetary cores take to form?
So the formation, the timescale is really, really fast, actually, because dust is collecting inside gas spiral arms in a very short time scale. And so you can see here is that in the time axis, so the collapse of dust happens in less than 1 orbital time. So it's a really fast and efficient process.
Just in the last thing when your planet was growing, and suddenly like grows fast. Do you understand?
Here.
Yeah, it has this period very fast.
Yeah, so what I guess is that at that point, the mass of the planet is high enough to undergo rapid accretion. So I think that at that point, so there is like a limit for, above which the accretion onto the protoplanet can be very, very efficient. And but yeah, we are still trying to understand better what happens. So what I actually think is that here I'm plotting the thermal mass, but probably the limit above which the accretion becomes really efficient is even before the thermal, so for masses that are smaller than the thermal mass. And it's like, I think it's happening like a runaway accretion at that point. But we are still looking into this.
So in your simulation, like you had that planet drifting inward, but you also had GI spirals and you had planet spiral.
Yeah, so here actually we are just simulating. So what we saw from our the previous work, so the planetary core formation, is that planetary cores are likely to form when the spirals are weak, because in that way they can't excite too much the dust particles. And so here what we are just doing is to simulate this planetary migration in a self-gravitating disk, so in a disk that is massive and where the role of the self-gravity is important, but the disk is not unstable here. So yeah, this is the main.
Yeah, I was like wondering if you could have, say like AB Auriga, you could have GI spirals, but also planet spiral, and maybe you could try to.
I think I mean I think it's going to be pretty tough, but I know that Sal worked a bit on planet migration in gravitationally unstable disks, showing that if the delta sigma over sigma of the spiral is too high, the migration is very efficient, and so it is really difficult to save planets in this case.